Okay, so now that we've talked about this old reaction with ethene reacting with HBr, we're going to try to make this example a little bit more complicated. So I'm going to get rid of this old mechanism. So now that we have this reaction kind of redrawn a tiny little bit, what we're going to do is take this ethene example and try to make it a tad bit more complicated. So what I'm going to do is redraw ethene, and then I'm going to add a little bit extra stuff. And then we now have two other carbons, 3 and 4. And so one thing to note is that this numbering scheme is completely arbitrary. This is just me numbering how I, just saw fit, just so I can talk about it. You could have called this carbon up top Bob and this one Harry if you wanted to. It doesn't really matter. This is just so we can communicate. So obviously this is a different molecule down below, and what we're going to do is react this new molecule with another hydrogen halide. So instead of HBr, let's try to do something just slightly different. We'll do hydrogen chloride instead. So the fact that we're changing bromine to chlorine really isn't that big of a deal. It's same kind of reactivity as the bromide overall. It could have been a bromine, chlorine, iodine, whatever. It doesn't really matter so much. But what we're going to do is try to react this new molecule with HCl and try to predict the product. So go ahead and pause the video and see if you can predict the final structure for this molecule. Okay, so the first thing that you should have done was you should have remembered that going from the alkene to the final product, we went from an alkene to an alkane to alkane. And so what we need to do is get rid of that old 2-to-1 bond, so we now have a single bond. And if you followed the template from up above, just like we added bromine to carbon 1, you could then say, oh, okay, I need to add chlorine to carbon 1. And I'm just going to draw it like this. I could have added the chlorine up above. I could have drawn it like that, or I could have drawn, down low like this. Doesn't really matter so much because, this 1 to 2 carbon can kind of rotate in free space. So not really worrying so much about that. As long as you have chlorine on carbon 1, that's what's really important. Okay, so if we wanted to put chlorine on carbon 1, we can also worry about, well, okay, where did that red hydrogen go? So if chlorine went on carbon 1, you can identify the other carbon that used to be made up, make part of the double bond, and replace that with your hydrogen. So if chlorine goes on 1, the hydrogen must go on 2. So this would be your hydrogen right there. Okay, so just like this hydrogen went in carbon 2 for the example up above. So this is a fine answer. This is perfect. This looks great. But there's a slight issue to attend to. So going back to this old example up above, let's say we had this molecule and we put the bromine on carbon 1 and the hydrogen on carbon 2. I'm just going to copy and paste this molecule and kind of redraw. We said that the bromine was attached to carbon 1, but really that's not the only potential outcome. So the bromine could have gone on carbon 1, or according to our mechanism, it didn't really notate which carbon the bromine was attached to. That's one inherent issue with this arrow bond notation, is that you don't have a specific carbon that you're adding to. So another way you could have drawn this molecule is that bromine could have been on carbon 2 instead of carbon 1. If you had done it this way, there's really no difference at all, because you could see that this is a symmetrical molecule 1, but we could have also rotated this molecule and bromine could be on the right, and this methyl group for carbon 1 would have been on the left. So really there's no difference between this molecule on the left and the molecule on the right. It's the exact same molecule. But whenever we transition from something very simple, like the top example, to something more complicated, like the bottom example, we're going to find that there's a slightly different outcome depending on which carbon we put that chlorine on. So down low, we said if we followed the template up above, that chlorine could have gone on carbon 1. But this is not the only possible product. There's a second possible product that you could get out of this reaction. So go ahead and pause the video. Again, try to figure out and draw out what the molecule should look like. Okay, so I'm going to assume that you actually did pause the video and try to write the molecule out on your own. And so we said that really 2 outcomes could have happened. So we could have either added chlorine to this carbon 1, or we could have added chlorine to carbon 2, because that initial, carbon to hydrogen bond forming process wasn't really explicit about which hydrogen got attached to what carbon. So let's go ahead and draw the other potential result, is that red hydrogen could have been attached to 1. And if that red hydrogen was attached to 1, then the chlorine must be attached to 2. And so now, if you compare and contrast, obviously this is a totally different molecule. And this is actually a very difficult point for students to grasp at the very beginning. So just to make sure it's absolutely explicit, let's go back, do the mechanism, and show just how non-specific this arrow pushing notation is. So the mechanism for this alkene reacting with a hydrogen halide is going to be composed of 2 steps. And the first step is that alkene acting as a base. And so that alkene is going to act as a base, and it's going to attack that hydrogen. And if we make a bond, we must break a bond. So if we break a bond, we're going to break that hydrogen to chlorine bond to prevent us from breaking the duet rule. We could have 2 possible carbons with a positive charge result from this push. And when we break that bond to make a new bond, with this arrow push, we're not really saying, okay, which carbon gets that red hydrogen. It's kind of nebulous. It's not really explicitly shown. So this is a very valid arrow push, but you could get 2 equally valid products out of it. We could have gotten this first molecule with a positive charge on carbon 2, and if that's the case, then that new hydrogen to carbon bond must be on carbon 1. So this is a very valid result of this arrow push, but it's not the only valid result from the arrow push. That arrow push could have also meant that we have that red hydrogen attached to carbon 2 instead. And if that's the case, then that carbon 1 has a positive charge. So if you compare and contrast, these are just, same thing as above, 2 different molecules, because that positive charge is on 2 totally different carbons. And again, this is the part that usually gives people trouble, which is that you have one valid, initial arrow push, and because of that one arrow push, you can actually get 2 different products, or 2 different intermediates in this case. And these are the 2 different totally valid intermediates that happen, which is you get this carbon with a positive charge on 2 and carbon with a positive charge on 1. Okay, so now I've kind of opened this door to talking about the mechanism of this more complicated example up above. Let's actually just finish up this train of thought just to make it really, really explicit. And all I'm going to do is kind of tack on the second part of the mechanism to what we already have drawn. And just to be really explicit that these are 2 different outcomes, I'm going to draw a little kind of dotted line between these. So this is maybe option 1, and this is going to be option 2 on the right. So in both options, we have a chlorine that's in solution in your flask or whatever, that's just kind of hanging around in liquid. And we're going to have that chlorine with a negative charge, just like the bromine had a negative charge. And that chlorine is really going to have 2 opportunities to do something. So in reality, what's happening is that both option 2 and option 1 are kind of explored by the initial molecule. So because both of these, carbons with positive charges are they're valid, they could result from the initial arrow push, they both will happen to a certain degree, more or less. So, and more on that in a second. But if both of these options actually do occur, then they both could potentially interact with chlorines that are in solution. So we can now subdivide these carbocations, these carbons with a positive charge on them, and talk about how they can interact with the chlorines. So we could said before that this molecule with a positive charge is going to end up being, we could categorize it as electrophile or a nucleophile. And this is going to be an electrophile because remember, electron, phile, loving, electron loving, and you always love what you don't have. So this carbon would love to have some extra electrons, so those are going to come from the chlorine. And so we can finish up this arrow pushing mechanism by having the chlorine attack carbon 1, and we can have this next option. This is just this opposite scenario, or alternative scenario for option 2, is that chlorine could also potentially attack and form a new bond to carbon 2. And in this case, we've pretty much finished up the second part of the mechanism for both options. So in this option 1, chlorine could attack 1, and that means that chlorine makes a new bond to carbon 1. That's what results. And then the option 2, chlorine could form a new bond to carbon 2. And if that's the case, this is the other molecule that results. So again, we have really the same molecule starting out with this molecule right here. It's going to do the exact same arrow push to form these positively charged intermediates, either option 1 or option 2. For either of these options, they are going to give us a different product. And again, just as this is another term that's kind of being introduced, so I might as well spell it out just to make sure you have an idea what it actually is, just in case I'm talking too quickly. But these two positively charged molecules are called intermediates. These are intermediates. They're intermediates because they are not the final molecule that we get. So they're kind of an intermediary between the beginning and the end. Okay, so these final molecules up above, this is the end of the novel, this is the beginning of the novel over here, and this is kind of a little bit more of the guts about what's happening inside of the novel.